It's time now to introduce the last speaker of today's webinar is Professor Amadeo Benavent-Climent from the Technical University of Madrid, Spain. His speech is about the use of anti-seismic devices. Professor Amadeo Benavent-Climent is PhD in structural engineering from the University of Tokyo in 1998. He's professor in earthquake engineering at the Technical University of Madrid and deputy head of the Department of Mechanical Engineering. He is coordinator of the Master in Earthquake Engineering, Dynamics of Soils and Structures. He's the president of the Spanish Mirror Subcommittee Eurocode SC8. He's member of the Spanish Committee AEN-CTN 130 Eurocodes. Member of European Committee CENTC 250 SC8, member of the International Committee ISO TC 98 SCC 3 WG9. Selected by the European Union as member of Project Team SC81 for next generation of Eurocode 8. His main research interests are structures with energy dissipation devices, energy-based seismic design, seismic response of RC structures, and health monitoring. He was principal investigator of 12 competitive research projects funded by national and international institutions. Professor Amadeo Benavent-Climent, welcome, and the floor is yours.
Thank you very much, Luca, for your introduction. Let me share the screen first. Okay. Well, thank you very much again. In this presentation, I would like to explain briefly everything related to the use of anti-seismic devices in the next generation of Eurocode 8. The current Eurocode 8, as Philip said before, covers basically only the base isolators in buildings or bridges, but there are other types of anti-seismic devices, such as the energy dissipation dampers and dissipation devices that have been increasingly used for the passive control of the structures in the last 2 decades. And these new technologies can easily accomplish one of the main goals of the current paradigm of the performance-based design, that is to control, to prevent or to dramatically reduce the damage in the main structure after a severe earthquake. The general aspects on the use of the anti-seismic devices are addressed in the new Eurocode 8 in section 6.8 of part 1.1. And this section covers all type of structures, buildings, bridges, tanks, everything. And also all type of anti-seismic devices. That means that it includes rigid connection devices for shock transmission, for guide and restraining movements, or mechanical fuses. It includes also the 2 types of energy dissipation devices, the displacement dependent devices, which source of energy dissipation is friction or the plastic deformation of metals, and also the velocity dependent dampers that dissipate energy by increasing the temperature of a fluid or a viscoelastic material. If we combine energy dissipation devices with a main structure and with auxiliary elements that connect the main structure with the dampers, we have what we call in the Eurocode 8 the structure equipped with energy dissipation systems. On the other hand, if we combine seismic isolators with energy dissipation devices, if needed, and with a superstructure and a substructure, we have a base isolated structure. So the section 6.8, as I said before, is general and establishes the basis of design for this type of structures. And I would like to point out several key aspects that are common to all type of structures with energy dissipation with anti-seismic devices. First, it is required an increased reliability to the anti-seismic devices, are also to the connections with the main structure, And this is accomplished by multiplying the displacements, velocities by a factor gamma x, which value is 1.5 or 2. Also, an important condition is that all auxiliary elements of the energy dissipation system must remain always elastic. Otherwise, the efficiency of the energy dissipation devices would be jeopardized. In case of base isolated structures, the isolation system must present some recentering capability and provide also sufficient lateral restraint in order to limit the lateral displacements or deformations. As for modeling, since the properties of the anti-seismic devices can vary with a given rate, it is necessary to conduct always multiple analyses in order to bound the effects of these variations. So let's move on to the analysis methods. The new Eurocode 8 covers 5 different analytical methods to obtain the effects of the seismic actions on structures with anti-seismic devices. The response history analysis can be used for any kind of structure, for structures with full or with partial isolation, or for structures with energy dissipation systems. The fundamental mode equivalent linear response spectrum and the multi-mode equivalent linear response spectrum are used in structures with full isolation. And finally, the multi-mode nonlinear response spectrum and the energy balance-based analysis is used for structures with energy dissipation systems. Now let me explain the main features of each method in more detail. The fundamental mode equivalent linear response spectrum analysis is similar to what is called simplified linear analysis in the current Eurocode 8. In this method, the superstructure and the substructure in case of buildings or the deck in case of bridges are assumed perfectly rigid, as rigid masses. In this case, the higher modes of the superstructure and of the substructure are neglected. The structure is assumed to respond predominantly as a single degree of freedom system in its horizontal direction, but it must be taken into account the torsional effects about a vertical axis. In this method, the isolation system is modeled as an equivalent linear single degree of freedom system with an effective stiffness and an effective damping ratio that is calculated with this well-known equation of dynamics. Here, the effective stiffness is obtained from the second stiffness of the isolators in case of buildings, and also from the, including also the contribution of the displacement stiffness of piers and the translation and rotational stiffness of foundations in case of bridges. And here, EDI is the energy dissipated by each anti-seismic device in one cycle of displacement at the period, at the frequency of the mode considered. Since the effective stiffness and the effective damping ratio depend on the design displacement, it is required to conduct several iterations until the tentative displacement assumed at the beginning of the steps is similar enough to the displacement obtained with this method. The next method is the multi-mode equivalent linear response spectrum analysis that is also in the current Eurocode 8. It's what is called in the Eurocode 8 the full model analysis. In this case, the superstructure and the substructure are represented by flexible, elastic, three-dimensional models. In this case, of course, the higher modes are considered. And for the first modes that involve deformations in the isolation system, that is in the anti-seismic devices, the response is obtained by representing the structure as an equivalent single degree of freedom system with an effective period, TF, and with an effective damping that is calculated as before from the energy dissipated by each anti-seismic device in one cycle at the frequency of the mode considered. As for the response in the higher modes that not involve deformations in the isolation system, the response must be obtained using the damping ratio of a non-isolated structure. And the response in each mode is obtained as usual through the response spectrum analysis. Now let me add some few comments about the more general method, that is the response history analysis. Some of them have been already pointed out by Matthias. This method can be used for all type of structures. It is important to use constitutive relations of the anti-seismic devices that must reproduce correctly the behavior in the range of deformations and velocities of the design seismic situation. In case of structures that are near fault, each pair of horizontal input motion components must be rotated to the fault normal and to the fault parallel directions. And the maximum damping ratio that is allowed in this method is 3%. Okay, everything that I have explained so far is applicable for general structures with any kind of anti-seismic devices. Now I am going to focus on particular types of structures that are covered in other parts of the new Eurocode 8. Let's start with the buildings with full base isolation, which are addressed in chapter 8 of part 1.2 of the new Eurocode. This chapter, in fact, is very brief because most of the information is provided in the general part of section 6.8, and only brief and few conditions are added. For example, in the case of using the fundamental mode equivalent linear response spectrum analysis in buildings, it is necessary to satisfy these conditions that you have here that are similar to the conditions that are already implemented in the current Eurocode 8. And for the seismic action effects, when calculating the seismic action effects on the superstructure and on the substructure, a Q factor of 1.5 can be used that accounts only for the overstrength. Of course, since we are dealing here with full base isolation, the plastic deformation capacity of the structure, of the substructure and superstructure is not included. Let's now turn our attention to the bridges with base isolation that are covered in chapter 8 of Eurocode 8 part 2. This chapter also includes very few additional requirements. One is that the superstructure must remain always elastic. And in the case of full isolation, the superstructure should be designed as non-dissipative, I mean, with utility class 1, except for heavy piers in moderate or seismic or high seismicity regions where ductility class 2 is required. Now let's continue with the verification of buildings with energy dissipation devices. This is a new topic that is not covered in the current Eurocode 8 and is addressed in chapter 9 of part 1.2. Since it is new, within the time constraints of this webinar, I am going to explain the verification of buildings with energy dissipation systems in a little more detail. First, two types of dampers are considered: the devices that depend only on the displacement and the devices that depend on the velocity and in some cases also on the displacement. This case is, for example, this is the case of the viscoelastic dampers. The displacement dependent devices include the friction dampers and the metallic or hysteretic dampers that I mentioned before, and the velocity dependent devices include the viscous and the viscoelastic dampers. The basis of design is exactly the same for the both types of energy dissipation devices. and can be summarized as follows. A building with energy dissipation devices is composed of two systems that are working in parallel. That is, they are subjected to identical lateral displacements at each floor level. These two parts are the main structural system and the energy dissipation system. The main structural system includes the primary and the secondary structural elements, and its primary role is to sustain the gravity loading, and optionally, if the designer decides to mobilize that, the main structural system can contribute also to dissipate part of the seismic input through plastic deformations on the primary structural elements. Allowing some plastic deformations on the main structure can reduce the demands on the energy dissipation devices, and therefore to reduce the cost of the energy dissipation system at the expense of increasing the reparation cost of the main structure after a severe earthquake. On the other hand, the energy dissipation system includes the energy dissipation devices themselves and all the auxiliary elements that must transfer the forces from the main structure to the damping devices. The energy dissipation system can be external or can be internal, and may have no shared elements, some shared elements, or all elements in common with the main structural system. So the main verifications or requirements for both types of damping systems, velocity dependent and displacement dependent, are also exactly the same. There are two main requirements or two main verifications that have to be checked. Concerning the main structural system, it must be verified that the energy that the primary seismic members of the main structural system at the each story, the energy that these elements can dissipate in this story before reaching the significant damage limit state must be larger or equal than the maximum energy dissipation demand on the primary seismic members of the main structural system on the story under the design seismic action. As for the energy dissipation system, the main requirement is that the energy that the dampers at the K story can dissipate before one of them reaches the significant damage limit state must be larger or equal than the maximum energy dissipation demand on the dampers at the K story under the reference seismic action. So these main verifications are done doing or using two different methods. One method is the nonlinear response spectral analysis that is used for buildings with velocity-dependent dampers, and the other method is the energy balance-based analysis that is used for buildings with displacement-dependent dampers. In both cases, in order to apply these methods and in order to apply also the simplifications that are involved in both methods, it is required that the floor diaphragms are rigid in their plane. It is required also to install at least two dampers in each direction and in each story, and they must be arranged, preferably in the perimeter of the building, in order to provide torsional stiffness and resistance. In the case of velocity-dependent dampers, it is also necessary that to apply this method that all the dampers are of the same type. Similar requirements are applied for buildings with displacement-dependent dampers. So both methods have also in common the following aspects. First, the overall system, that is the main structure and the energy dissipation devices, is assumed to dissipate energy through plastic deformations only in the first mode. Only in the first mode. First mode means here the vibrational mode with largest effective modal mass in the direction under consideration, in the direction of the ground motion that is being considered. And second, in the higher modes, the overall system is assumed to remain elastic, and the response is obtained through conventional response spectrum analysis. Okay. Okay, now I would like to give you some background information about the nonlinear response spectrum analysis that is used for buildings with velocity-dependent dampers. The nonlinear response spectrum analysis is a combination of the nonlinear static analysis that Matthias has presented before and the response spectrum analysis. It is largely based on the capacity spectrum method proposed a long time ago by Freeman. In this method, the response in the first mode is obtained by idealizing the overall structure with an equivalent single degree of freedom that has an effective stiffness, TF1, and an effective linear viscous damping ratio, GF1. This method is appropriate for structures with velocity-dependent dampers, since their main source of energy dissipation is of the viscous type. That is the same nature as the effective viscous damping that is used in this method to represent the dampers. However, this method is questionable for structures with displacement-dependent dampers, since in this case, in the case of displacement-dependent dampers, the main source of energy dissipation is of the hysteretic type. That is, it's the plastic deformation of elements. And there is no physical principle that justifies the existence of a stable relationship between the hysteretic energy dissipation of the maximum excursion and an equivalent linear viscous damping, particularly for highly inelastic systems. And we have to have in mind that these type of structures are highly inelastic, since the energy is dissipated by large plastic deformations on the, or mainly through large plastic deformations on the displacement-dependent dampers. Well, this is a controversial issue that has been largely discussed in the literature. And it is one of the reasons, why for buildings with displacement-dependent devices, the more straightforward approach of the energy balance based method has been adopted instead of the method used for the velocity-dependent dampers. So let's now focus on how the nonlinear response spectrum analysis method makes the energy verification of the main structural system. That is, how the energy that the primary seismic members of the K story, the energy that these primary seismic members can dissipate before reaching the significant damage limit state is larger than the maximum energy dissipation demand. In this method, since this method does not provide a quantitative estimation of the energy dissipation demand on the main structural system at each story, the verification must be done indirectly through the following steps. First, the main structural system must be classified as utility class 1, 2, or 3, depending on the compliance of the conditions that are stated in clause 6 to 7 of part 1.1 and in sections 10 to 15 of part 1.2. This classification gives or determines the maximum allowable Q factor for displacement, the maximum ductility factor QD. Second step is to calculate the displacement ductility demand, that is called here mu F, that is defined as the maximum roof displacement in the first mode divided by the roof displacement at yielding. And the yield displacement, the roof displacement at yielding is obtained with this simple formula that can be obtained from simple considerations and is explained in the background document of this part of the Eurocode. And finally, the third step is to check that the ductility demand μF is smaller or equal than QD. So next slide shows how the maximum roof displacement in the first mode is calculated with this nonlinear response spectrum analysis. This is done by idealizing the structure with the velocity-dependent dampers with an equivalent single degree of freedom system with period TF1 and with damping ratio GF1, similarly to what I explained before in reference to the base isolated structures. So the procedure, the steps to obtain this maximum displacement at the roof in the first mode is first to obtain the capacity curve of the main structural system through a pushover analysis or using approximate approaches. Second, to adopt a tentative value for the roof displacement in the initial steps, and to obtain the corresponding values of the ductility factor, the effective period, and the effective damping ratio by using these equations that seem complex, but in fact they are not complex at all. They can be obtained from basic considerations of dynamics and are explained also in the background document of this part of the Eurocode 8. Third step is to calculate the total base shear of the structure by summing up the base shear of the main structure corresponding to the assumed roof displacement plus the elastic force sustained by the elastic component of the dampers in case of viscoelastic dampers. In case of viscous dampers, this component does not exist. And four, we calculate this theoretical base shear by applying the well-known equations of dynamics of the response spectrum method. And we have to check that this value is close to this theoretical value to be sure that this point that we have selected is on this curve. Okay, next main verification is the one that affects the energy dissipation devices. We have to check that the energy that the dampers at the K story can dissipate before one of them reaches a significant energy limit state is larger than the maximum energy dissipation demand on the dampers of this story under the reference seismic action. In this case, the verification is done directly. The problem is that this method, this nonlinear response spectrum analysis, this method does not provide a quantitative value, a quantitative evaluation of the amount of energy that has to be dissipated by the dampers in each story. So in the lack of this information, we made the following conservative assumption, that is to assume the worst case scenario. This worst case scenario is that all the energy input by the earthquake, removing the energy dissipated by the inherent damping of the structure, concentrates in a single story. And this is the energy that is obtained with this equation. So we have to check that the energy dissipated, that the capacity of the dampers in each story is larger than this value. Okay, besides the main energy verification explained above, it is necessary also to make additional verifications on the structural elements of the main structure and on the auxiliary elements of the energy dissipation system. More precisely, we have to verify that the design value of the seismic action effects, what is called here ED, is smaller or equal than the design resistance. ED must be calculated for three different stages of the structure. First, the stage of maximum displacement. second, the stage of maximum velocity, and third, the stage of maximum acceleration, because we don't know in advance which will be the worst scenario. And this is accomplished by developing in general a three-dimensional elastic model of the structure, and subjecting the model to a series of forces that are given by these equations. I am not going to enter in detail due to time constraints. And with this analysis, we obtain ISCs, the value of ED for each member of the main structural system, and also for each member of the auxiliary energy dissipation system. Now, finally, let's focus on how the energy balance-based analysis makes the verification of buildings with displacement-dependent dampers. The energy balance-based analysis, in this method, the hysteretic energy is not represented by an equivalent viscous damping ratio. The problem is addressed directly in terms of plastic strain energy. This method is based on the conservation of energy and the works of Hausner, Akiyama, and others, and it is ideally suited for application to structures employing energy dissipation devices, because for these systems, a proper energy management is a key to a successful design. In this method, the designer is not concerned so much with the resistance to lateral forces or with the lateral displacements, but with the product of both, that is, with energy. And not with monotonic energy, but with cyclic energy. The designer directly and explicitly controls and decides how the energy input into the structure from the earthquake is distributed between the main structural system and the energy dissipation system. And this method, as you will see, allows a quantitative control of the damage on both the main structure and the dampers. Okay, the energy dissipation capacity, that is the main verification concerning the main structural system at the K story, is done as follows. We calculate first the energy that the primary seismic members at the K story can dissipate, the amount of energy that these elements of this story can dissipate before reaching the significant damage state. And we have to check that this energy that is called here EPHKSD is larger or equal the maximum energy dissipation demand on the primary seismic members of the main structure at the K story under the design seismic action. It will be called here EPHK max. This verification can be done in two ways. There are two alternative ways. A direct verification, that is the recommended verification and the most rational verification, or an indirect verification that is similar to the one that I explained before for buildings with velocity-dependent dampers. So let's start with the direct verification that involves estimating the energy dissipation demand on the primary elements of the main structure of the K story, this value. This is done by using this formula that you have here, that were developed by Akiyama, and that are implemented, are basically the same implemented in the current Japan building code. Here, EHK is the total plastic energy dissipation demand on the K story, and it is obtained by distributing the total energy input, that is the total energy input that contributes to damage, that is this value, minus the energy that can be stored in form of elastic deformations by the structure. We have to distribute all this energy in brackets among the stories. And this distribution is made using this law that was proposed by Akiyama that depends on two factors, on two parameters. One is pk. pk is a parameter that represents the deviation of the strength of the K story with respect to an optimum value that would make the damage, the normalized damage, equal in all stories. So this parameter represents the deviation of lateral strength with respect to an optimum value. And the second parameter, PTK, depends on or takes into account the proneness to torsion of the building and is obtained in function of this ratio that is the equation between the distance between the center mass and center stiffness and this torsional ratio. Once we have the amount of plastic strain energy demand on the K story, we have to distribute this energy between the primary elements of the main structure and the energy dissipation system and the energy dissipation devices. And we do that with this very simple equation that assumes that the energy, the total energy, plastic strain energy in the story is distributed between the main structure and the dampers in the same proportion of these areas. This approach is quite conservative. I mean, it gives tends to give an overestimation of the damage on the main structure, but has the advantage that is very simple, and that's why it is used. Well, once we have the energy dissipation demand on the main structure, we have to compare it with the energy dissipation capacity of the primary elements of the main structure, the K story. It's important to point out that these energies we are comparing are cyclic energies. I mean, are the energies input by the earthquake, not monotonic energies obtained from a pushover analysis. The capacity, the energy dissipation capacity of the main structure, the K story, EPH-KSD, must be determined from the cyclic response of the structural members or subassemblies obtained experimentally, and the deformational strength models that are in clause 7 of part 1.1 can also be very useful to have a lower bound of this value. As I noted before, these deformational strength models of clause 7 provide the response on the monotonic load and the monotonic loading. I mean, the maximum plastic rotation, for example, or the plastic hinge. But here we are dealing with the energy dissipation capacity under cyclic loading. But this value calculated with these equations can be, is in fact a lower bound of this value, and in the lack of cyclic tests can be used to make this evaluation. So, if the designer does not want to make this direct verification, that is, as I said before, the recommended approach, an indirect verification can be done exactly the same as I explained for structures with velocity-dependent dampers. I am not going to repeat it. The main difference here is that the roof, the maximum roof displacement, is calculated also from energy considerations by assuming that the total energy that must be dissipated through plastic deformations on the K story is dissipated through a single cycle of amplitude equal to the maximum interstory drift. So once we have the maximum roof displacement in the first mode calculated, we check the same condition as before. Okay, next we have to verify the second main verification affects the energy dissipation devices. In this case, the estimation of the energy dissipation demand of the dampers installed in each story is straightforward since the energy balance approach provides directly this information. And this demand, what is called, this is the energy dissipation demand on the dampers of the K story. This demand is evaluated as the sum of these factors. This one is the portion of this total energy that goes to the K story distributed according to the areas that I pointed out before. But we have to add also here this term that represents the energy that must dissipate the dampers in the cycles that the main structure remains in the cycles which maximum displacement remains below this value, that is the yield displacement of the main structure. And we have to add also in this approach the energy dissipated by frequent earthquakes. We assume here that before the design earthquake, the structure can be subjected to 5 low-intensity earthquakes, and the energy input by these earthquakes in the dampers is evaluated with this value that is taken also from the Japan Building Code. We have to conduct an additional verification on the main structural system and the energy dissipation system. The verification is that we have to check, we have to verify that under a low intensity earthquake, the dampers can plastify, but the main structure must remain perfectly elastic. I mean, below this point, that is the end of the linear portion of the main structural system. And this is done by comparing the energy dissipation demand associated with a frequent earthquake, that is taking as 1/4 of the energy input by the reference seismic action. This is compared with the total amount of energy that the main structure can store in form of elastic deformations, this term for the main structure, this term for the dampers, and the maximum energy that the energy that the dampers can dissipate through plastic deformations with maximum displacements below this point. Okay, finally, it is necessary to make also additional verifications on the structural elements of the main structure and on the auxiliary elements of the energy dissipation system. More precisely, we have to verify, similarly to the buildings with velocity-dependent dampers, we have to verify that the effects of the seismic actions are smaller or equal than the design resistance. And this is done also, this is done in case of displacement-dependent dampers. This is done only in the stage of maximum displacement. And it is accomplished by developing an elastic 3-dimensional model of the structure and applying these forces, which obtention I am not going to explain in detail due to time. Here you have some references, and this brings me to the end of my presentation. Thank you very much for your attention.
Thank you very much, Professor Amadeo Benavent-Climent. Thank you for the very detailed speech about the main novelties introduced in the second generation of the Eurocode 8 about the use of anti-seismic devices. So we have time now for some questions and answers by the audience. You're invited to either type your questions through the chat, or if you wish, you can also speak. We don't have questions so far. Maybe I have a curiosity. Meanwhile, you have mentioned the primary and secondary roles of the main structural system. What about the optional role of contributing to energy dissipation through plastic strains? Is there any indication of threshold of limitation, to which extent?
Sorry, can you repeat the question? I didn't.
You have mentioned the role of the main structural system.
Yes.
Structural system of the building.
Yes.
So you have mentioned the primary role of sustaining gravity loading, now we're subjected to lateral displacements, and then the secondary optional role. Now that it's left to the designer. And also, are there any indication about the damage limitation criteria?
Well, the Eurocode does not provide any indication about that, but the engineering judgment would advise to limit the plastic deformations on the main structure. Otherwise, it doesn't make any sense to use dampers. So it is reasonable to limit the ductility demand on the main structure to at most ductility class 2. I mean, QD up to, I don't know, 1.3, 1.5, something like this.
Okay.
From my point of view, it wouldn't make too much sense to go to ductility class 3 and to use dampers because it would be not really rational. But you can do it, of course. The designer can do it.
Okay. Thank you. There is Professor Philip Bish with the hand raised.
Yeah, if I can make a complementary comment about products. This is typically the case here, if I may. So it is a constant will from SEN that we have a complete compatibility with the other norms issued by other technical committees. Okay, and of course, Eurocodes are playing the leading role in the definition of the properties that we need. But it is a very vast program, which is not simple at all. I just want to say that for seismic devices, there is a very good relation with TC340 in charge of devices. And so we even have common members in both TCs. So in principle, we should have all the required properties for the analysis.
Thank you.
Thank you. There is a question by George Varelis. Thank you for the very interesting presentation. Alternatively to testing, can the energy dissipation capacity of a device be verified through nonlinear numerical analysis, like the finite element method?
Well, the capacity of the devices must be obtained experimentally through tests. And as Philip said, the product standard 15129 is the one that is expected to provide this information. I am correct, Philip?
Yes, exactly that. And we even have removed from Eurocode all the, you had an annex in, I think in part 2 about the testing of devices. We have removed that because it is in the scope of TC340.
And this is a very important information because other codes don't make this check. And in a structure with damping systems, the dampers are the responsible of the seismic resistance of the structure. So it's necessary to check that they will satisfy the demands, of course. Yeah.
So they have the list of the required properties that we need, and so it helps to them to develop the test to qualify the device.
Okay, I see another question by Anila Saisha. Greetings. Are the self-centering energy dissipation devices covered? Flag-shaped hysteresis? In case they are, what is the suggested analysis method?
No, they are not covered in the two methods that I explained in more detail. Of course, you can design with this type of dampers using the response history analysis, of course. And in fact, well, you could extend very easily the energy balance-based method to deal with this type of devices, with this type of smart materials. And I think that this person is referring to nickel titanium bars and things like this. No, yeah, it's very easy to implement that in the energy-based method. Very easy.
Okay, move on with the next one. Ian G. Smith from Atkins Tech, Deer Infrastructure. Is the reliability of EDDS comparable with that of the seismic structure?
Well, I think that the dampers, the energy dissipation devices, have a much higher reliability than the main structure. The dampers are made in under very strict quality controls in factories, while the main structure in case of reinforced concrete, for example, is prone to all type of execution problems and depends largely on the skills of the people that is building the structure. So from my point of view, the reliability of the structures with damping systems is higher than the conventional structure.
Okay, there is another question. Thank you for the nice presentation. The Japanese code uses velocity spectrum for the design of the isolators, but in Eurocode there is not any velocity spectrum. How can you solve it?
Yes, it is. I mean, these equations that I show represent the velocity, the response velocity that is calculated from the acceleration spectrum. And in fact, these velocity spectrums that are provided by the German building code are simply the acceleration response spectrum multiplied by the frequency to obtain divide by the frequency to obtain the velocity. So it's not explicitly provided in Eurocode 8 a velocity response spectrum, but it's implicitly adopted in the equations.
Another question by Thomas.
Oh. Well, yes, it is written in Eurocode, the new Eurocode 8, that the aging problem and the possible variation of the properties with the age must be taken into account. Yes, of course.
Good. There are no other questions so far. Okay, so it seems that your questions were clear enough, and thank you very much again, Professor Amadeo Benavent, for the very detailed contribution. Thank you for sharing. And well, I think we are on time to finish, to conclude.